All right, I'm back. I'm still on page 249. Let's see if we can get through a bunch of this. So we're going to keep going limit from the left, limit from the right. If those two are equal to each other, we can say that the limit exists and is equal to that value. Also, if you've seen Mean Girls at like the pivotal, I don't know, math, whatever, at that math competition, that's sort of what she says in her head. Like if you go back and watch that, it's a good movie. I kind of recommend it. I've seen it a lot because it's on cable a lot, and I used to be a cable person, you know. She says that, right? She's like, oh, if the limit from the left doesn't equal the limit from the right, then the limit does not exist. So go watch that. I just ruined the end of it for you, pretty much, but what are you going to do? It's like a 20-year-old movie at this point, you know, keep up. All right, so the limit as x approaches 15 from the left. From the left, what's to the left of 15? I always go through this in my head. 13, 14, 14.9, 14.99, 14.999. We're getting infinitely close. So I need to approach. So I'm going to start on the curve and just kind of go. So you can keep drawing the little stick figures. You don't really need to, but you could. So like your stick figure like this, and then blindfold. I feel a need to be consistent. Blindfold, and you're going this way. You're always going to be going that way in that color if I do this right, which I probably won't. All right, so that looks to me like 10. So when you get there, you expect to get 10. Turns out you do get 10. No one cares, which is a weird thing. You got to get used to it. So I get 10. All right, limit from the right. So what's to the right of 15? 17, 16, 16. Well, yeah, obviously 16 point something because that's between 16 and 17. I meant to say 15.5, 15.1, 15.01, 15.00000. Keep saying O forever. 1 is to the right of it. So we're going like this. And remember, you're blindfolded. Not my best stick figure. And you're walking this way. Blindfold. Going this way. What do you expect to get when you get there? You might fall off and plummet, but what do you expect? You're blindfolded and you're just going to step. I couldn't even do it. You're blindfolded and you're going to step, right? What do you expect to get? You expect to get 18. That's the logical Y value. It should be 18. For some reason, it's not. And the person walking from right to left is going to fall because of that, but it should have been 18. So that's our limit from, ew, wrong color, wrong color. Once you commit yourself to something, you got to follow through. So I think that's 18. Okay, now, if the limit from the left is 10 and the limit from the right is 18, then like they're not going to meet up. The limit does not exist. The limit as x approaches 15 does not exist. The limit from the left exists, the limit from the right exists, but they're not equal, so the limit overall doesn't exist. So we are going to say dne, I guess we're saying that in black, dne, which stands for does not exist. One time, one of my students accidentally wrote DNS on a quiz, and I like sick burn, right? I was like, does that mean did not study? And everybody was like, ooh. And like, yeah, admittedly, that's like, I probably shouldn't have said that, but you know, sometimes when the spirit moves you, like apparently it was just moving the screen. Okay, the next question is, what is f of 15? 15? 15. What is f of 15? F of 15 is the filled in dot. So f of 15 is right here. F of 15, it turns out, is whatever that number is, 10. So f of 15 is 10. So we have kind of an interesting situation here where the limit from the left is equal to the value of the function, but the limit from the right is not equal to it. There's a special name for that that we'll get to later in the notes, but the name for that is that it's continuous from the left. As you move from left to right, you actually get the value that you're expecting. So that's called continuous from the right. If you got the value that you were expecting as you move from right to left, it would be continuous from the right. If you get the same value for the limits and the function, then we just say the function is continuous at that point. So these are big ideas. that we're going to talk about a lot, but I think it's good to start thinking about them now. All right. So what is this? This is 20, I assume? 22. How's that 22? Okay, 22, because we're counting by twos. Limit from the left. Limit as x approaches 22 from the left. Like this. And when you get there, you would expect to get 4, I think. I'm counting by twos, pretty sure. I would expect to get 4. Let's deal with the right. So the limit, so to the right, and just, do it. Just go toward it. When I get there, I also am expecting to get 4. So this is exciting because if you get the same value both times, then you're able to say that the limit exists. So I'm going to say the limit as x approaches 22 of f of x is in fact 4. If f of 22 is also 4, then I'll say the function is continuous at x equals 22. So continuity is entirely defined by limits and the value of the function. If the limit exists and the function exists and the limit equals the value of the function, then a function is continuous at that point. That's a really important definition. It's called a 3-part definition. But look at this, we got a problem. F of 22 doesn't even exist. So I'm gonna write that it does not exist. So down here, is a DNE. And this is one of the things you want to start thinking about. Okay, so there are points on this graph where the limit exists, but the function doesn't exist. This is a good example of that. Removable discontinuities, it seems like, are examples of that. At 7, that also sort of happened, except the limit existed, but the function existed and was different. So that is still a removable discontinuity. It turns out the definition of removable discontinuity is a point at which the limit exists, but is not equal to the value of the function. And we're going to talk about that more in other notes also, so you don't need to write that down, but start thinking about that. At x equals 15, we had the limit from the left existed, was finite. Limit from the right existed, was finite, but they're not the same. That's a jump discontinuity. All types of discontinuities are going to be defined by limits. So we're getting there. We're getting a lot of math done here. 29. All right, 29. Let's go from the left, switch up our pen. I think that when I get there, I am expecting to get 8. That seems right to me. Right? Remember, you're blindfolded, you're just walking, you have a little faith in the process, and then the function is letting you down. So I don't know why you keep having faith in this process. From the right. Okay, so we approach from the right. Right? What's to the right of 29? To the right of 29 is 36, 33, 30, 29.5, 29.1, 29.01. You keep putting zeros in there, you're still to the right. When you take that final step to get to 29, you would expect to be at 4. You're not, but it doesn't matter. All that matters is what do you expect to get? You expect to get 4. We have a problem, right? The limit from the left was 8, the limit from the right was 4. So overall, the limit does not exist. So D and E. But both of them existed and were finite. Left and right existed and were finite. Well, I guess more like this. Left and right existed and are finite, which means this is a jump discontinuity. Discontinuities are all defined by limits. I'm like just repeating a lot of things. And then the actual value of the function is right here. So that's 6. It doesn't really matter. When you're talking about limits, this is weird. When you talk about continuity, the value of the function matters. When you're talking about limits, no one cares what the value of the function is. We're living in this perfect world. Like, what should it have been? What should have happened? And that's all we're trying to answer. All right, and then 40. 40 from the left. All right, well, check this out. Also, watch the PDF just keep going. From the left. Going, 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 going. There's no end in sight. It seems like it's just going to keep going up. In fact, it is going to keep going up. This is a vertical asymptote. As I go closer and closer to 40, the y values are going way up. So we're going to say that that limit is infinity. And also, I'm going to erase this thing because it's in my way. So this is infinity. Eventually, you're going to have trouble making infinities and 8s. I have more trouble making 8s than I do infinities because I make a lot of infinities, especially in like Calc 2. You do a lot of series stuff, and the upper bound is always infinity on the summation, those sigmas that we did in the last set of notes. All right, from the right, change of color. Here we go. Going, 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 going. And look at that. Going to negative infinity. All right, so let's fill that in. So we get infinity from the right and negative infinity from the left. Those couldn't be more different. They're as different as two things can get. So definitely the limit does not exist. Let me fill that in. Let's go back and look at the graph and see if there could be a random point. So these are always like piecewise functions or just random made up garbage. There's no point here, but you could, like, there's no reason there couldn't be a point. You could just put a dot on this graph at like 40 comma 6, just like fill in a dot, and then f of 40 is 6. Limit from the left is infinity. Limit from the right is negative infinity. That's like mind-boggling. A vertical asymptote and the function equals something there? Like, what? That's a new idea. Piecewise functions let you do basically anything. Does not exist. So let me say one more word about this, though. If the limit from the left and the limit from the right were both infinite, so like this, or if they were both negative infinity, like this, if they're both going to infinity, I would have said the overall limit is infinity, which would have given you a lot of information. It would have told you that the graph basically, and I don't know that I would write this down, it would have told you the graph looks like this. If both limits were negative infinity, I would say the limit overall is negative infinity, and the graph would have looked something like this. So you just get more information by knowing these limits. And that's a big idea. Like we want to be able to like draw graphs and things like that. So there's not much left on this page, so I'm just going to finish it. One thing, this is perhaps a pet peeve of mine, but also entirely incorrect to ever do. Never, ever, ever should you write like a naked limit. Look at this. The limit as x approaches 29. You know what someone's going to say? They're going to say, of what? The limit of what as x approaches 29 is 4. Of what? Writing limit as x approaches 29 without a function there, and you're probably going to do it, and it's going to drive me insane, and then you're going to never do it again because of the reaction that I have. The limit as x approaches 29 without anything there is just like saying sine parentheses, nothing in there, close parentheses, equals 1/2. Like, sine of what equals 1/2? Now we happen to know that, but if you don't fill it in, that's the issue. Treat it like a function. The limit as x approaches 29 of something is equal to something. You have to have that of there, or it's totally meaningless garbage. So don't do that. Let's fill these in. So this in words, the limit as x approaches, so many words, c from the left. But if you don't know these words, you can't talk about it intelligently, and you basically can't talk about it. Of f of x is 3. That's really the only way. You could also say the limit of f of x as x approaches c from the left is equal to 3. Like you can, they're clauses. You can like take the two clauses and switch them if you want. And I think I do that when I talk, but when I write, I usually don't. So this, I'm going to use notation. I'm going to say that this means 1, the limit as x approaches c from the left of f of x is equal to -10. And 2, the limit as x, you get this information for free. As soon as someone tells you a limit, you know the left and right hand limits. Unless they tell you it doesn't exist, in which case you don't know anything. Other than that the limit doesn't exist, which is still useful. But both of these limits, ooh, -10. Both of those limits must be -10. It's the only way you're allowed to say that. What you don't know, do not know f of c. That, you have no idea what f of c is. F of c might be -10 and the function is continuous. F of c might be 53 and the function has a removable discontinuity. You just have no idea. There's not enough information to tell you anything about what f of c is based on the fact that the limit as x approaches c of f of x is -10. That just means that the blindfolded person walking from the left and the blindfolded person walking from the right both think that they're going to put their foot at y equals -10. It doesn't mean that when they do that, they're not going to fall through a hole. All right, so I'm going to stop this here and come back in another video and keep going. So I hope you're finding these helpful.